There it goes. All right, so yeah, we're going to continue chapter 2. And the course videos that I kind of said for chapter 2, they're just going to be the class videos. So I should have them recorded and put on YouTube and then put onto D2L. So you should be seeing those kind of as we're going along. But I should cover most of the material, and then we should have time. I'll probably stretch it into next week. We'll probably do Monday next week. We'll do some example problems similar to what you would have for homework. The chapter 2 homework is posted. It's going to be due on the 15th of September. So make sure to get started on that. Go ahead and start by writing, going to the homework connect down, looking at the problems and then kind of writing them out, at least starting with the knowns, unknowns, and kind of the free body diagram you expect. But it is due on 9/15, which is a Tuesday of next week. So you guys have about a week to complete the homework. And then the following Wednesday at 6 p.m. is when the exam 1 is going to be held. And so make sure to get on board with that. And so it'll be open book, open note, whatever resources you have, except, of course, Chegg or whatever. You're just going to be looking at the problems from D2L. Or not D2L, but you're going to look at the problems. I'll probably have it posted on a video, and you'll have your camera on, and I would want to see your camera on your notes, so like what you're writing out, and so I can see your hands basically, and whatever textbook or whatever you're using, that's fine, but we'll kind of do it that way. We'll see how it goes. If everybody gets 100%, then if there's something else, then I have to kind of restructure. So anyways, so that's the first exam that's going to be covering chapters 1 and 2. So that'll be the homework that you've been doing so far. Do I have any questions before we get into today's material, which is the agenda is right above my head. We'll start off with Poissons Ratio. Let me get the chat open. I'll try to look at chat periodically. All right, so kind of a review from last class. We're dealing with chapter 2, which kind of introduces the concept of stress-strain relationship and axial load. One of the things that we talked about beforehand is that the major assumptions we are going to make in this class going forward is we have homogeneous and then we have isotropic. And so homogeneous, what does that mean? You can unmute yourself or type in chat.
Is that a single body?
Single body, not so much. But when we say for the context of this class, when I say a material is homogeneous, what does that mean?
It's one solid.
It's one material, right? It's not specifically. It's saying there's no difference spatially throughout the material. The big thing is like the difference between a chocolate chip cookie versus a sugar cookie, right? So we're dealing with sugar cookies in this class, not chocolate chips, right? Chocolate chips is that some points in space you might have chocolate, some points in space you have cookie. That's kind of the point here. It's an important distinction because there might be some materials you would work with where that doesn't hold true. The other one is isotropic. So what does isotropic mean? Are you guys even here? What's going on?
Is that the XYZ plane?
What's that?
Is it the way it sits in the XYZ plane?
Not so much that. It's an assumption we make about material. So here it's specifically about the material. We say that there's something about the material and we call it isotropic. So it's similar to homogeneous, where homogeneous is spatially, you don't have any points. But isotropic means based on direction. So there's no changes based on direction. So that's what isotropic means. It's uniform regardless of which direction you're in. A good example of a non-isotropic material would be wood, because the grain of the wood kind of dictates how strong it is in certain directions, right? So if you've ever been involved in construction using wood, it's very important how you cut the grain. So that is a non-isotropic material. So a lot of times this lends itself to really kind of like metals, things like that. And that's where most of the material you're going to be working with in your homework, at least starting off with. So yes.
Sorry, I had a question.
Yeah.
Isn't some steel work to be like layered, and does that not change how it behaves?
So typically steel is worked down. It is worked to a point where it's still homogeneous and isotropic, right? I'm not familiar. There might be more advanced machining techniques if they have kind of steels of different quality or grade at different locations. Do you know what I mean? Even when you fold steel and you do the annealing process or whatever, it's typically restructuring it so that it is consistent throughout. And the idea is if you're buying like stock material, you get it off the boat or the ship or whatever, and your block or your ingot of steel, that you assume it's the same throughout. In fact, it's typically specified to be the same throughout. But a lot of this is geared towards construction materials. So we talked in class a little bit about, we've done this a bunch of different times, and we would expect if we load up a part that is fixed to a wall, okay, and here I've got a coordinate system aligned with the axis of this cylinder, and we would then say, all right, if I were to be analyzing this, I can say, well, we can define my stress, right? It would be axial stress in this case, down the x-axis, or we can think of it as sigma x. That would be equal to whatever my load P is divided by the cross-sectional area. And that cross-sectional area could be just rewrite. We could say P over, and then it would be like pi over 4 d squared, the way we have it written. And we know that from Hooke's law, right, we could say that this sigma x then would be related to E, right? And we're assuming it's isentropic and homogeneous. Yes? Sorry. Somebody have a question? No?
I think someone just walked into the room where they were.
Okay. So we have the E, which is what? What do we call E?
Young's modulus of elasticity.
Yeah, so Young's modulus or modulus of elasticity. Typically, you don't say Young's modulus of elasticity. It's too much.
I was looking at data sheets for PLA yesterday.
Right.
And they had something, it was weird. They didn't have Young's modulus, they had tensile modulus.
Right, and so that's similar. So I would say it's so the idea is that there is a modulus of rigidity, which is sometimes it's used for shearing, and we'll talk a little bit about that in a moment. But that's probably referring to this relationship here, because plastics to a certain extent can be assumed to be what we call linear elastic, right? So if it abides by Hooke's law, this is a linear relationship. You should know that, right? So E here is just a variable that's dependent on the type of material, and epsilon x would be the deformation right along the x direction. But we also can understand that, if I were to pull on this long enough, okay, there would be a deformation that occurs kind of in the diameter direction, right, or the lateral direction. And this relationship between the strain we would expect to see, in the along the axial direction versus the lateral, there is a relationship between those two, and we certainly will talk a little bit about that. Okay, and so the first person to really observe this relationship is a French mathematician, Poissons, right? Simon Poissons, and that's the same guy that Ely had brought up. He's a mathematician. He's very popular. But this idea of if I were to be pulling on a piece of material, right, with the load P, I would expect if I were to take any block out from this piece here, I could then qualify it and say the stress is going to be the same across the surface. We'd say we are assuming that load P is applied in such a way where the stress is consistent. We do not expect to see any stresses in the X and Y, or I'm sorry, the Z and Y directions based on our reference points here. But that does not mean we're going to see no strain. So the strain that comes into play, even though the stresses are considered to be zero, there will be strain in those directions. And so we are assuming that's where we say the homogeneous and isotropic. And the good way, a very simple way of putting it in like layman's terms, is that there's no directional dependence or spatial dependence. It's all the same material every direction. These strains are not going to be zero. So that's going to be an important aspect to understand. Poissons ratio is used, and we use this Greek letter. Does anybody know what this Greek letter is here?
Nu.
This is nu. And the way that I write out nu, it looks like a V, right? So it can be confused with V. So I typically write out nu as almost like having like two curls, that we kind of see that's there. And that's really exaggerated. A lot of times it'll look something like this, right? And so it's a ratio of strain. So what's the units? What are the units of nu, or Poissons ratio?
Unitless?
This one is indeed unitless. Then there's no like special units like millimeter per millimeter or anything like that. This one is indeed unitless, and typically it's going to be bounded. It's going to be around 0.3 for a lot of steels or metals, but it's always going to be less than 0.5, right, or less than and equal to 0.5. And I think you have to look into some theory of elasticity. So what this relationship is it's a negative quantity, and then we say the lateral strain, right, which is the strain in the direction out of the plane, and then the axial strain is on the bottom. And so in the example of my cylinder, now we have this quantity, this relationship where we say, okay, let me get rid of now. Sorry, that's been up there.
I was about to say something.
Yes, feel free to stop me and tell me. Okay, good. Unitless. Yeah, news unitless. All right, so here we've now got Poissons ratio, which is equal to, and we got to remember there's a negative here, and then they have like the absolute quantity, right, of the. Now in this case, if we're doing in this particular direction, I can choose either or. So the lateral strain. So say for instance, I'll say epsilon y over epsilon x. That would be my relationship for Poissons ratio. Now, why is there a negative here? Why do you think there's a negative that's put there? I'll look at chat or just guess.
Do you have to do something with the graph? Or
well, let's think about what's going to happen here, right? If I have strain where this is starting to come out like this. So say, for instance, this part is elongated, right? So that means I would have epsilon x is positive, correct? It would be positive strain because it's elongating. Remember we said if it elongates, it's positive strain. If it contracts, it's negative strain. You can have negative strain, right? You can, right? What would happen if epsilon x is positive? What's going to happen to epsilon, we'd say y?
It would shrink a little bit.
It will shrink, okay? So think about it, if you take a rubber or a sheet of rubber or something, you pull on it, right? You'll get long in one direction, but it's going to get smaller in other directions. That's why the negative is set up. A better way to kind of look at this is I'd say, okay, the epsilon x is equal to negative nu epsilon y, right? So if I have a positive relationship for epsilon x, I should have a negative for epsilon y. Does that make sense? There has to be a negative. There's going to be a reduction in quality there. I'm sorry, reduction. Now, one thing you have to recognize, it's conservation of mass, but it's not conservation of volume. In fact, the volume that you expect to see, right, you would kind of want to guess that you say, all right, so if I'm given the way they're showing this here, is that this was the original shape where the dashes are, and this is the new shape, so to speak, where it's already been strained. And remember, we're not considering the dynamics. We're only considering after the loading has taken place. So if the shape was originally in the dashed line, right, there's going to be contraction. Now, in an ideal case, it won't be completely uniform, but here we're just assuming that it is. Like it's going to be complete reduction. In this case, you can, if you were to have this relationship, you can use it for both epsilon y and epsilon z, and it's always referred to by the axial strain, and the axial strain is defined by the fact that we're working with axial load. So this is going to be when you're pulling on something along an axis, so it's always dependent on that. The volume will change. There will be a change in volume, okay? And so that's touched on a little bit afterwards. But the important thing to remember, this is something that you should just know right off the bat. I shouldn't have to say, if you're working a problem out, and I say, well, tell me what the change in the lateral dimension would be, you would then go through and model it, and you should know Poissons ratio. This is something that's also categorized or cataloged in appendix. Is it appendix D? That's what I remember from last class. It's shown. It shows up with like this yield stress and so on and so forth. Okay. So that's important quantity to follow through, and there's some homework problems that are based on that. The next section describes what we call generalized Hooke's law, right? And this sets up some relationships that will be helpful in the homework and certainly on the exam when you're given this kind of three-dimensional setup, and you were to say, all right, if we're understanding, and this idea of principle of superposition. So if you're taking notes, this is something you really want to write down. And it's going to hold true for the rest of the class. In fact, when I was talking to Dr. Adams about this class, he was asking about it and kind of like, well, what's the point of it, or what do people really get at? And if I had to have one statement about this class, it's we're using principle of superposition. What is principle of superposition? It's this idea that we're working with typically very small deformations relative to the size of the original object, and also we're working with loads that do not go past what we call the proportional limit. So what is the proportional limit for a material?
Yield? No.
You're on the right track. And a lot of times yield stress, right? If we're coming back to our stress strain diagram, this is my sigma and this is my epsilon. For a given material, you have a linear relationship, and then it at some point it stops becoming proportional. Okay, so when we say proportional limit, it's no longer proportional, meaning it no longer has that linear relationship. And so if we go past here, we cannot use principle of superposition. But if we are living in this region right here, right? Remember, when sigma is equal to E epsilon, if we can use Hooke's law, we can use superposition. At least it's one part of the problem. The other thing that we talk about with principle of superposition is that for multi-axial loading, if you have different loads, and this is the case for shear as well as bending and really any other type of problem, the second axiom here is saying that we have to make sure that the deformation resulting from any given load that is small, and it doesn't really affect the conditions of the application of other loads. What does that mean? Well, let's consider over here, let's consider a beam that's kind of sitting off the edge of a fixed wall. And if I were to put a significant enough load down at the end, so now we're not dealing with axial loads, but this is probably my best way of illustrating this relationship, is to say, well, if we understand the forces, if it's large enough, think about a diving board, right? If I had a diving board, I would put a load on it. I would expect to see it do something like this, right? So now, if I have the same load P, right? I drew it bigger, so technically it should be the same. If I have the same load P, and P is just in such a way that it causes this to kind of deflect downwards so much that, right, if we assume this is the same location, right, now we're at a new location, right? And so what's happening there is it's changing. If I were to do a free body diagram for this and this, what's going to be different because of that position of the force moving the moment exactly, right? So it's going to change. It's not going to change the axial or the transverse loads, right? It's going to change the moment. And if it changes the moment, then it's no longer static, right? It's technically it's in such a way that there is some change in the relationship. So this typically occurs when we see excessive deformations. And so a lot of times the way that I think about it in this class is in order to use principle of superposition, you're linear elastic. And typically if you're linear elastic, right, unless you have a very big elastic range for a material, especially with metals, you'll also satisfy that you're not going to see it really, say, a significant change in the positions of the load. That's what I think some people are asking before. It's like, well, if you were to add the strain in there, technically it would move it enough that it would be a change in the moment. And you could actually calculate that change in the moment. It's going to be such a small value that it really doesn't matter. Okay, so if those two cases hold true, which is they are major assumptions, then you can use principle of superposition. Well, what is principle of superposition? What that represents is now I can consider, say for instance, I have a load in different directions, and that's why they talk about this idea of multi-axial loading, right? Meaning I have loading in the Y and the X and the Z, right? If I have different axes, I can consider these problems as 3 different problems in X, Y, and Z, and then add together the strains that develop. And this is going to be the same thing when we get into shear or bending. We're going to get at the end, when you get all used to all the different loadings and what kind of strain they're going to develop, you can then just add all those strains together. Same thing goes for the stress. And so when you go, I'm not going to go through the derivation. The derivation is in the text, but you can think about it. If I want to find epsilon x, well, I know generally from Hooke's law, I have, well, it should be just sigma x over E of the material. Remember, E is isotropic and it's a homogeneous, so it's going to be the same in any direction. But you also have to consider that there will be some change in dimension from the stresses that are occurring in the Y and the Z directions. And so you're going to have a homework problem where it's going to give you this complex loading structure, right? It's going to tell you there's stresses in each direction. It's going to tell you what's the overall change in the dimension. Well, you're going to have to come back and look at this relationship here. And you could use, so on an exam, if you wanted to have this as be like your theory, you can certainly start off with that. Now, a lot of times what'll happen is, maybe you won't have one of these stresses. Maybe you don't have stress in the Y. You can ignore that or say it's 0, but you have to consider the fact that there's stress in the other directions. And this just comes in, and this is where Poissons ratio shows up, right? It always shows up in the out of axis stresses, okay? If I have, in this case, X, we know that the relationship for strain in the X is just going to be nu Y or nu sigma Y or nu sigma Z. Does that make sense? Is that clear? All right. So this is kind of it's a small section, but it's really important, is understanding this idea of superposition and when we can use that. All right. Any questions so far? Okay. So I had mentioned before that I was going to, that any of the chapter sections that have a star next to them, we're not going to cover in this chapter. That's section 2.6. I think that's the first one that shows up with a star, except I think for one of your homework problems, you need to use this relationship, which is called the dilatation. And all it is, you just have to know what that relationship is. It's just summing up all of the epsilons for the X, Y, and Z directions. And what that represents is the change in volume per unit volume. That's why it's a dimensionless quantity. And the way you would find the new volume, if you want to find delta V, you would just say this lowercase e multiplied by the original volume V. Yes.
What is that small e? Is that just...
It's called dilatation.
Okay.
And that's in this class, that I guess they're using E specifically for dilatation. It's not exponential or anything else. It's just...
Okay.
And that's it goes to the text. We're not going to spend time on this, but it does show up, and I will say it shows up a little bit kind of going down the line. Okay. You can also find it by relationship with other factors or whatever, but we're not going to kind of get into that. All you have to know is that it's really this thing here. That's kind of the change in volume would be the epsilon, or I'm sorry, not epsilon, but it's just E, right? Multiplied by the original volume, right? Because really, if you want to think about it, E is just delta V over the volume, right? Change in volume, delta V, per unit volume, V. Is that clear? Okay. And here they show the bounding for nu. because of that relationship E. Anyways, so you'll never see, if you ever use nu larger than 0.5, you're doing something wrong. Okay. Especially, I think there are problems that say calculate what nu is. And so you may on an exam and say it gives you the strains or information about the strains. You might have to calculate what nu is.
No, that's just unrealistic values, or
No, it's like physically cannot occur.
Okay.
By ratio, by changing the direction. The way you calculate that is you look at like how things are going to strain. All right. So the next section in the textbook talks a little bit about shearing strain, and shearing strain is kind of the next level. So when we start talking about different loading, right now we're talking about axial stress, and axial stress won't develop shearing strain unless you change your orientation, right? And we'll talk about how some loading conditions will develop shearing strain. What is shearing strain? Well, we know that the quantity for shearing stress is tau, and it kind of gives that sliding motion. So we'd expect if I have an element that's under pure shear, and we talked a little bit about, if this is an equilibrium, then these tau values should be the same at all points, right? If we satisfy equilibrium, they should be the same. We calculated that before. That's from chapter 1. Okay. But what kind of strain are we going to see from the shearing stress? Well, let's kind of simplify it a little bit. And the textbook kind of does this with this picture down here. But a lot of times the way I think you can almost simplify it by saying, let's start off with the original shape. And then we say, all right, well, let's consider that the shearing stress are going to look something like this. And so it will change the geometry. It's going to change in various directions, but it's going to change the geometry to look something more like this. And I wonder if there you go. Right? Now, this is, of course, very exaggerated. But how do we define the strain in this case? Axial strain, it makes sense. If you have a length change, we'd expect that to be axial strain. But shearing strain is a little different because now it's a change based on angle. And the way we define the shear strain is that, say, for instance, I take a horizontal line here, right, which would represent the original position of this element. The angle that we see here is this Greek letter or this. What is that Greek letter?
Gamma?
That's gamma. Okay. Now, for shearing strain, it's very dependent on the plane you're working with. So typically what we'll do for shearing strain is we always identify the plane. In this case, that's my y, and this would be like my x, so I call it my xy strain. And a lot of times what you'll see as it defined by is that you'll see it defined by this angle. And that's what they're doing in the textbook, where they say it's pi over 2 minus gamma xy. Which if you're following at home, you recognize that this angle here is 90 degrees, and so the angle of the new material will be related to the 90 degrees. Now, remember, the gamma, that's always going to be in radians. Okay? Always use radians for gamma. You can, at the end of the day, you can put it back into degrees to get a functional feel. I've been using radians for a while now. I still don't have a functional. I know pi over 2 is 90 degrees, but if you give me some fraction of radians, I'm like, I don't know how big that is. Or in this case, if you give a numerical value, a lot of times we report it in radians of numerical value. I don't really get a good feeling. But degrees, we kind of have a better understanding of. So you can always transmit it back to degrees if you really want to figure out how big these strains are. Now, just like we have Hooke's law for stress, this becomes our strain, right? That's our relationship for strain. And so now for Hooke's law, we could say that the shear stress will be equal to some quantity, right? Some proportional factor, like we have Young's modulus for axial or normal strain. And then we put the shearing strain there, and the letter we use is capital G. And capital G, it should be really, there's two names that we kind of go by, is modulus of rigidity, right? Because G is now, before where E is more of a function of how things will displace in a given direction, G is one for shearing. So now if we expect to see kind of sliding motion, so it's going to tell us how rigid a material is, and that's why we call it modulus of rigidity. The other one we also call it is shear modulus, and I might use either term on an exam, but you should immediately understand that this is G, right? And so Hooke's law now can be applied in all directions, and it also shares there is technically like a proportional limit, so it will be linear to an effect, and in effect, it will share a similar curve to what we see here. Now it's not as categorized, and sometimes a lot of what you would do is you would say the yield stress for axial and then the yield stress for shear is roughly the same, but they may not be depending on the material properties. Okay, so just like the stress-strain relationship for axial stress and strain, we have the same kind of treatment for shear stress and strain. So let's look at an example of how we would use this. So if I were to take a block, okay, of some material, and it just tells us we don't know what the material is, but it gives us G, which is what?
90 KSI.
Okay, yes, it's 90 KSI, but what is G? Not you, Ely. Somebody else.
Shear modulus.
The shear modulus. It's modulus of rigidity, right? So it's telling you when you see that in a given problem statement, you should be knowing, all right, we're going to be calculating shear. All right, it's bonded with two horizontal plates, and these plates are going to be rigid, I believe. The lower plate is fixed, and the upper plate is subjected to the horizontal force P. Knowing that the upper plate moves through 0.04 inches under the action of the force, determine A, the average shearing strain in the material, and the force P that's exerted on the plate. And so doing this example, this is the easiest problem you're going to run into for this type of work, but you're going to have homework problems that are similar to this, in which you'll have to determine, start off with the geometries, and you go through. And the solution procedure here, kind of thinking ahead, you say first we can determine the average angular deformation because we're given something about the geometry, right? We're given the information about the geometry. The top plate is moving 0.04 inches, which is a very small value. It's very small. So a lot of times in these types of strains, because we're assuming linear elastic, same thing goes for this quantity here. We're working with very small angles. So what is the small angle approximation?
Sine theta is equal to theta, right?
Right. So in small angle approximation, we can say sine theta is equal to 0. What about tan theta? Not 0. It's equal to theta. I think I said 0 by accident. What about tan?
So it's blasphemous. That's
Sorry.
what it is.
Sine theta is equal to theta. What's tan theta equal to?
Theta over cosine theta?
So what's cosine of a very small value?
1. It'd be 10.
So what's tan theta?
1.
Theta.
Theta.
Because it's theta over 1.
Exactly. So here, sine and tan theta, this is small angle approximation. And if you don't want to use small angle approximation, you're certainly welcome to try to do it. But what you're going to find is that it's a small angle approximation in these cases are very good. We can use this relationship to solve this problem. And that'll help us out. And then also we're going to have to apply Hooke's law for shearing stress to determine to figure out what that shearing stress will be. And then that's how we're going to determine P. Right? So let's go through and solve this problem. So we have our knowns. The known problem is G is equal to 90 KSI, which is kips per square inch. We know the deformation would say, let's just call it delta, of the top plane. I'm just going to call it delta for right now, 0.04 inches. No other numbers there. We have the information, right? So I'm going to just call back to that information. We have the picture there. So our unknowns, part A is looking for the average shearing strain. So we're looking for the gamma. Okay. And this would be gamma, we'll call it xy. Okay, because assuming we'll put a coordinate system that looks like this on the material, it'll be the gamma xy. And then it's looking for the force P. Right? And so my diagram here, not really, I'm not going to do a free body diagram, but we're going to do a diagram. I'm going to simplify this, and we're going to have, let's draw a rectangle. Oh. It's not wanting to do a rectangle.
It doesn't like it.
There, it figured it out. All right, we're going to start off with the original shape. And we know the top plate is going to move over a certain amount under that load P. Remember, we're not considering the dynamics. We're just considering that it has moved. In this case, the new shape is going to look like this. Right? And so for our solution, I guess theory and solution here, we can get, we should understand that the gamma of xy, in this case, let me make sure I have the coordinate system labeled. Use this. That's my y. That's my x. And this here would be my gamma xy. Gamma xy should be equal to the tangent of whatever this value is. So this distance would be my delta, and then this distance was what? 2 inches, right? So let's call this quantity, let's be general, h. So the theory here is that it should be equal to the tangent of opposite over adjacent, so that would be delta over h, but we know from small angle approximation we just call it delta over h. So here my gamma xy would then be equal to delta, which we said is 0.04 inches over 2 inches, which is equal to what?
0.02.
0.02, and that's going to be radians. If we wanted to find this in degrees, we could say that's equal to 0.02 radians multiplied by 180 degrees divided by pi radians. Radians will cancel out. So what is that in degrees?
9.
Is it 9 degrees?
3.6.
What is it?
3.6.
3.6 degrees. Which I think small angle approximation, what's the minimum angle there? I guess do tan, you know,
4 degrees.
It's something. So what's tan in degrees for 3.6 degrees?
Oh, wait. No.
If it's in radians, what's tan of 0.02?
It should be 1.14 degrees.
Oh, is it 1.14?
I forgot to divide by pi.
That's why I was like, that seems a little high, but maybe it's on the edge of what. So what's tan of 0.02? In radians, if your calculator's in radians, if it's in degrees, what's tan of 1.14?
0.02 radians.
Okay, so yeah, as you put 0.02 tan, and if it's in radians, you get 0.02. So that tells us that that small angle approximation is okay here. Anyway, so this is what it was asking for. Technically, that's the answer for part A, right? The average shearing strain. That's just by geometry. The next part, part B, the theory here is then Hooke's law. Remember, we had shear stress should be equal to G multiplied by gamma. G is given to us. Gamma we already found, but we're trying to relate that back to its load. And so here, looking at our picture, the load P is what's causing that shear, right? So then we can rewrite the theory to say that should be whatever value P over the cross-sectional area. In this case, if we say this is our like width, and this is our like length, and we can come back over here and say this is G gamma, then our P over length times width is equal to G gamma. And then my load P would then just be equal to length width G gamma. And so P would then just be equal to length and width, we said is 8 inches multiplied by 2.5 inches, and then multiplied by G, which is 90 KSI, which we say times 10 to the 3 pounds per inch squared, and then multiplied by gamma in this case is multiplied by 0.02, right? So what is my load P? And this is going to be in pounds, right? Because my units cancel out here. What is that P?
36 KSI.
What is it?
36 KSI.
I got 3,600 pounds.
3,600?
Pounds, yeah.
So what's wrong with 36 KSI? What's immediately wrong with that?
That's
Because it's not a pressure.
It's not
It's supposed to
stress.
be a, yeah.
So here we use stress. In this class, we talk about stress, right? So it's not a stress. It should be, this is a load. It should be in just straight either pounds or newtons or whatever. But that's an issue there. So is it 3.6 times, or so we'd say 3,600?
pounds.
Okay. So it would take 3,600 pounds to get this material to shear over like this. And think about it, 3,600 pounds, that's a lot. That's like the weight of my car or something, you know? That's the amount of load that's needed to make this move 1 degree, right? So you can kind of get a feeling that we are working with typically, you know, loads in such a way that it kind of makes everything a little bit easier to work with. Do I have any questions on that? And if you have questions about this, this is literally worked out in the textbook for you, but it will help kind of going forward. Do I have another question?
Question about shearing strain.
Yes.
Does it have a similar property of superposition? Or
Yes. Yes. So so superposition is allowed for stresses and strains of any type. And by any type, I mean the two, you know, normal or shear. So, yes, it's because, and what we find, and this is going to be the next section we talk about, that if I look at a problem, right? If I look at something where I say these two are the same cases, the only thing that's different is how I drew my original shape. For instance, if I draw this dash block as my original shape before the load is applied, and I pull on it, this new shape is what it shows up, okay? And then you can go through, you can find the geometry here, you recognize the relationships in the axial and the lateral directions, you can find their geometry is great. You should be able to do that after reading the textbook, going through the concept, then you're gonna have homework problems that do exactly that, great. But what if I had drawn my shape 90 degrees different? So nothing has changed about the material or anything else, the loading or anything else. The only thing that's going to change is the way that this shape is going to change. The way you can think about it is that if I were to draw a vertical line and a horizontal line, those would change in the same way as the one before, okay? Meaning this vertical line is going to get smaller and the horizontal line is going to get larger. And that's what's happening that we see here, right? This vertical line gets smaller and the horizontal line gets larger. And so naturally, there will be a shear strain that shows up, okay? And the only thing that changed or different is that with the way we're orienting our element. And so that can be one of the more confusing aspects about stress and strain, is that even though we're dealing in this case with an axial load problem, there is technically can be calculated a shear stress. And that's important from a design standpoint, because say, for instance, a material is not very good at shear stress versus axial stress. Well, you still have to consider for even what you would think is a pure axial loading case, there is shear stress in there that the material feels, right? And so we can relate just by geometry, right? We can relate E, which is your modulus or Young's modulus of elasticity or Young's modulus, nu Poissons ratio, and G, the modulus of rigidity or the shear modulus, because we can then look at the geometries here. And I'm not going to go through the math. The textbook does a pretty good job of showing that relationship. I'm not going to do that here. But ultimately what you have to remember is that if I'm giving a lot of times, sometimes you'll have a problem. I might do this on an exam where I give you like a problem where you have to solve axial load, and you've done that earlier. And then I might say, all right, also, what's the shear stress at this one point? And I won't give you G. I'll just give you E and Poissons ratio. Something like that. And then from those relationships, you should be able to determine what G is and then go into the shearing aspect or using the shear stress aspect to kind of solve problems. So it's important. This is an equation that you should have written down and would be handy on an exam. Right? Section 2.9 is not covered. Section 2.9 is one of those starred sections. It deals with composite materials and it doesn't. It just has some generalizations we're just not going to cover in this class. But if you're interested in that, that's certainly that. Then of course, then there's the composite materials means you're not going to have homogeneous or technically isotropic. So let's look at another example problem. So a sample problem, if we have, so now looking at this case, right? So if we have a stress on a plane, kind of like a plate we're working with, there's a sigma x that's going along the x direction, there's a sigma z, and it gives us these stresses. So it tells us the stresses that are in these directions. It also tells us that a circle that's drawn out, this ABCD circle, has a diameter of 9 inches. Also, a thickness of 3.4 or 3/4 of an inch. It says it gives us the force acting on the plane. It gives us E and Poissons ratio. So the next thing it asks, it says, all right, what is the length of the diameter AB? What is the length of the diameter CD? The change. That's important. I was like, it's just 9 inches, right? No, it's asking what is the change in length for AB and CD. Also, what is the change in the thickness of the plate and the volume of the plate? Okay. And so when attacking these problems, you say, all right, well, first off, we know that for these two cases, because we have stress in the x and z directions, can I just say that, well, we know sigma x is equal to E epsilon x. In this case, really, if I find the epsilon x, I should find that the value AB prime, right, should be equal to whatever the change in epsilon x multiplied by AB plus AB, or another way to write this is you can say 1 plus epsilon x AB, right? But I've got the sigma. I could just put this value in here and not consider anything else. Is that correct? Would that get me a right answer? Obviously not, because I'm asking it in such a pretentious way. What am I missing here? What is going to cause strain in the x direction outside of just sigma x?
Oh, well, if you pull it in the z direction, then it'll.
Yes. If I remember, principle of superposition means I can treat this as two different problems. I could treat it as taking away this and just looking at this case, but then I have to also consider the case where we're just looking at sigma x. If I just had sigma x, this analysis is completely fine, right? The length change in AB would just be the elongation. But because we have a stress in the z direction, I also have to consider it. It turns out we have a relationship. We can find this exactly. And that's back up here with this guy right here. Right? This would be the equation I'd start off with. And like I said, if you just say, all right, this is just asking me what's the new length in the x direction, we'd say, okay, well, we can find epsilon x because we have sigma x, we have sigma z, and we're not considering sigma y. And I can do the same thing for epsilon y and epsilon z. Then I just have to basically apply, and in each of these cases, there's no sigma y. I just have to figure out what those stresses are. But they all come back to nu and the property of the material E. And hopefully, just by doing that, you should recognize, or you should understand, and I know I'm running out of time here, that if we go through the analysis here, and the book does this, that's all it does, right? It says, all right, we can find epsilon x by putting in all those values. Remember, the sigma y doesn't exist, so I don't put that value in. I get a value for my engineering strain in the x direction. Remember, this is the strain. This is what I was calculating before. That's from sigma x and sigma z. I can then do the same thing for epsilon y, epsilon z. I get 3 different strains. And so then when you're trying to determine what the change in the diameter would be, you can find what, I think it is asking what the change in the diameter is, right? Then you could just multiply that value by the diameter. Because remember that the diameter is going to be the original length AB. And the same thing goes for my change in Z. And then the last one, the thickness, is just my epsilon y multiplied by its original thickness. And then the very last part of this, which is, like I said before, is what we would need from that one section, was if you calculate the dilatation, which is just the sum of all the epsilons, you get a non-zero quantity. So while it may be interesting, or you may want to infer that there will be no change in the overall volume, there is a change in the volume. And that's because we see local changes in density. Right? The mass still stays the same, but we'll have changes in density. And then you use the change in the volume would just be E multiplied by its original volume. That's how you get the values there. So I think if you go through the sample problems, you go through the conceptual problems when working the homework in this particular part of Chapter 2, that should get you to the point where you should be able to work the problems out. And of course, what we'll do is we'll work some example problems either on Friday or Monday, in which I'll work problems throughout the chapter. And of course, if you have any questions, we can always work during office hours, or you can set up a Zoom call, whatever you need. But start on Chapter 2 homework today. Start working it out. Try to stay ahead of things. So when I ask you what stress is, you don't just like wait for somebody else to answer. Okay. Okay?
Lesson learned last week
Yes.
on Friday.
Okay.
7 and 8 give me a run for my money.
Exactly. And so it seems simple the way I'm describing it here, but it can get complex the way you apply everything. Okay. All right. Any questions?
No.
What about this class?
All right. So I'm going to stop the recording now.